In the previous lecture, we talked about challenges of word learning and the most commonly cited theoretical accounts that try to explain not only the core task of learning the meanings of words from noisy data, but also trying to explain the developmental patterns that have been observed in children when learning the meanings of words. So what we are going to do today is to look at three computational models that have been proposed as modeling some aspect of word learning. So you will see that the models have different architecture. They actually come from different modeling frameworks, which I deliberately chose to show you how these frameworks actually work in action. And they focus on different experimental or empirical findings and try to explain them. So together they might give us a larger picture of what might be plausible to assume about mechanisms that children use to learn words. So let's start by the connectionist model of Terry Regier. This model was developed in 2005. It's a simple associative or connectionist model. The architecture is to some extent similar to the very generic architecture of the multi-layered connectionist models that we looked at before, with a twist. So what you see here is a model that has 4 layers on the two ends. So on the left-hand side and on the right-hand side, you see layers that are connected to the outside world, and then you have 2 hidden layers in between that connect the outer layers. I don't call the outer layers input units and output units, or input layers and output layers, because this model actually is bidirectional, so it can receive a phonological form of a model of a word and then generate its meaning representation, similar to what we do when we hear a word or when we perform comprehension. But it also can receive the meaning representation and then generate the word form, similar to what we do when we are producing language. So in that sense, each layer at the outer side can act both as input and output in different scenarios. Now, similar to any connectionist model, there are connections between units or neurons between each 2 consequent layers, and these connections have different weights. The weights perform different functions. So between the, say, phonological form and the next hidden unit, or the meaning representation form and the next hidden unit, you have weights and connections which basically determine how much attention the model will pay to each of the features in the phonological or meaning representation of a word. And we will talk about this a little bit later. And then between the hidden layers, you also have connections with different weights, and these are simply called associative weights because they determine to what extent a form is associated with a meaning. So how is the input and output represented in this model? The phonological form is simply a vector of phonological features. For example, whether a particular phoneme is voiced or not. And the meaning representation is again simply represented as a vector of semantic features, for example, the shape and the size and the color. So in that sense, the representation is very similar to examples that we already saw when we were discussing connectionist models. So what Regier does is it actually trains the model by giving the model a phonological form, let it predict the meaning representation, and then gives it feedback. If the model has made errors, then the model has to readjust all these weights so that next time it sees the same form, it can generate the correct meaning, or at least generate something that's closer to the correct meaning. And it also does train the model from the other side. It gives it meaning representation, lets it produce phonological forms, and then adjust the weights based on how far the predicted form was from the correct or ideal form. Now, if you look at the ease of learning, so the amount of error that the model makes over time, you see on the x-axis the number of rounds where the model is trained, and on the y-axis the amount of error that the model makes. And you see that at the very beginning the model makes a lot of error because it doesn't know anything, so pretty much all of the predictions are wrong. But then gradually it learns, and it actually learns pretty fast to produce the correct forms, and so you see that the error drops dramatically. So that means that the model is actually learning. But what is it that the model is learning? This is a very interesting experiment that they performed. What they did was they looked at the weights for connections between the input-output layers and the hidden layers. I told you before that these can be seen as how much attention the model pays to each input feature or to each output feature. And interestingly, the model learns very quickly to pay more attention to features that are relevant. For example, for meaning representation, shape is almost always relevant, whereas color is not necessarily relevant, or size sometimes is not, and sometimes it is. And you can see in these graphs the weights that the model learns for phonological features and for semantic features. At the beginning, all of these weights start from the same place. They're all around 0.3 because the model really doesn't distinguish between different features. But over time, it learns that some of these features are more informative than the other in predicting the correct response, and therefore it increases the weight for those features, whereas for the other features, for the useless features, it decreases the weight. And so you see this beautiful separation between significant features and non-significant features, which is something that also can be observed in humans. You see that all the infants are pretty much sensitive to most of the phonemes, but then they lose their sensitivity towards the end of the first year in response to phonemes that are not present to their mother tongue. So they don't really pay attention to those distinctions anymore. And finally, Regier performed some experiment on learning second labels, and it shows that if the model is presented with a novel word, then at the beginning it does perform poorly, but it gradually learns the meaning of the word pretty well, and that's the dashed line. That's the probability the association between the novel word and its meaning, and you see that it increases relatively quickly. Whereas if you actually introduce it with a word form for a familiar concept, so if you force the model to learn a second label, then it really doesn't do well, at least not as well as learning a completely novel word, and that's the solid line. So let me wrap up what this model really does. It makes certain suggestions. It suggests that if we use a simple associative learning mechanism for associating the phonological features to a meaning representation, then at first you might be slow, but it actually becomes much easier as the time passes. So as the model sees more and more input, it learns faster. It also shows that sensitivity to various features can be learned from input. The model can actually, over time, distinguish which features to pay more attention to and which features to ignore. And also the experiments on learning second labels mimic beautifully what we have seen in children, which is at first the model cannot really learn these second labels as easily as they learn novel words. What are the limitations of a model like this? Well, first of all, words are treated in isolation, so the model doesn't hear sentences. It receives each word paired with its own semantic representation. It simplifies the problem massively. We talked about the challenges of word learning, and this is a main challenge, to learn words within a sentential context. And also, learning is not incremental. The model has to be trained over a large set of input over and over again in order to recognize these patterns. So now I want to move to actually much older model. This is a symbolic rule-based model proposed by Jeff Siskind in 1996. This is a relatively rigid model, but because it is symbolic and has all the limitations of the symbolic frameworks, but it was actually one of the very first models that managed to show certain patterns that can be learned just from the input. So this is how the input to the model looks like. The model receives an utterance together with a bunch of potential meanings that this utterance might refer to. So it's trying to simulate referential uncertainty in its input. And then it gradually learns meaning representations for each word. So words appear in sentential context, but the model is trying to learn the meaning of each individual word. So you see that the meaning is learned in terms of two sets of meaning elements. So one of them represents all the necessary elements, so the components that we know have to be part of the meaning of a word. And then the second set shows possible meanings. So ball could be, the symbol ball could be part of the meaning of the word John, based on what we have seen so far, but we are not sure. So a word is learned when these two sets are identical. All the necessary meanings are part of the possible set, and all the possible meanings are also part of the necessary set. So how does a model learn? It basically starts with putting all the meaning components as potential meanings for all the words. So each word has a very large possible set of meanings and an empty set of necessary meanings, because we don't know anything about the meanings of words yet. And then every time the model receives a sentence associated with its potential meanings, it applies a set of rules to update these two sets for all the words in that sentence. I'm going to show you an example rule. For example, for each word symbol in the utterance, rule out any conceptual symbols that do not appear in some remaining utterance meaning. It means that if you have a word in a sentence for which there is no... sorry, let me explain again. It means that if some of the meaning elements have not appeared in the current input item, then they cannot be part of the meaning of the words in the sentence. So if I hear the sentence, John went to school, and these are the meanings that are associated with it, then none of the words can mean a chair, because a chair didn't appear anywhere in the space of possible meanings. So that's how you, if chair was before part of the possible meaning of John, then you remove that based on this rule. So if you do that, you apply these rules over and over again on all the sentences, then you see that these curves show how the model learns over time. So on the y-axis, you see the size of the vocabulary, all the words that the model has learned. And on the x-axis, you see the number of utterances that have been processed so far. So the more sentences the model sees, the better it learns. You can go and take a look at Siskind's paper that I have put as part on the list of reading material to get more details about it. This graph shows the age of exposure effect. It shows how many times a model needs to see a particular word until it learns it. On the x-axis, you see the number of utterances that the model has heard prior to the first exposure to a new word. And on the y-axis, you see number of occurrences that are needed for that word to be learned. And what you see in here is more or less a fast mapping pattern. You see that at the very, very beginning, so a very young age, the model actually needs to hear a word several times before it hears it. But once they learn something about the language, they actually need only one or two occurrences of a word before they learn it. So if I want to summarize what Siskind's model does, it basically is suggesting that the change in the learning rate can be explained purely based on a cross-situational learning mechanism. So you don't need to switch the underlying learning mechanism in order to explain why a sudden change in learning rate happens. It also shows that as the model learns more words, it can use its knowledge to rule out meanings that are not part of words, and therefore it increases the speed and efficiency of learning the meaning of new words. So these are interesting findings, and there are some limitations to this model, obviously, the most important of which is that the model assumes a noise-free input data, which is absolutely not plausible. And that's because of the symbolic nature of this model. It also doesn't take frequency effects into account. So even if we hear two words at very different frequencies, one of them only a couple of times, the other one 100 times, once we learn the meaning of them, the confidence of the model in those two words is the same, because the model really doesn't have a mechanism to show its confidence based on past experience. The last model that we will look at is the probabilistic account of cross-situational learning. So this is a very general scheme of what a cross-situational learning model would look like. It receives input that consists of pairs of utterances and their semantic representation of some sort, and then it generates some sort of an association between words and their meanings. So the model of Fazli et al., which was proposed in 2008, tries to implement this mechanism, but instead of just taking a strict rule-based approach, it wants to take probabilities into account. So the input to the model is a set of utterances paired with a set of features that represent the meaning in the scene. And the ultimate representation of knowledge in this model is a probability distribution for each word. So for each word, we learn how probable every meaning component is as part of the meaning of this word. So let me show you an example to make it a bit more clear. On the top of this slide, you see 6 sample utterances that contain the word ball, and you see for each utterance the scene that was associated with it, so the visual context in which the utterance was uttered. And then at the bottom of the slide, you see how the probability distribution that the model learns for the word ball changes over time as it receives and processes every single input item. So at the beginning, the model doesn't know much about what ball can mean, other than the fact that it can mean any of those meaning components that appeared in the first scene. So you see that all of those meaning components have equal probability as part of the meaning of the word ball. But this distribution changes gradually as the model notices that more and more consistently the word ball co-occurs with the symbol ball. So you see that the probability mass kind of accumulates around the correct meaning, which is the symbol ball. So how does the model learn this? It actually uses a 2-step learning mechanism, which is very simple. So at each step, it receives a pair of a scene and an utterance. And then the first thing it does, it tries to align words in the sentence with meaning components in the scene. If up until this point the model has learned that, for example, the word apple and the meaning element apple or red are strongly associated with each other, then it hypothesizes that the reason they co-occurred in this particular input item is because they are actually related. Another hypothesis another bias the model implements is that if it knows that the meaning element is part of the meaning of another word in the sentence, then it doesn't really strongly align it with a new word. So there's a soft version of the principle of mutual exclusivity implemented in this model. So once its alignment scores are calculated, it updates the meaning of every word in this current sentence based on this alignment score. So the probability distribution is slightly adjusted. Of course, all this is done based on some mathematical formulation, which is not really our focus, but that's I explained the basic principle behind these formal steps. So what do they show? They first of all show that if their data contains referential uncertainty, then learning is going to be much more difficult. So the purple line shows the performance of the model, which is basically the proportion of words that are learned when there is no noise and no referential uncertainty in the input. And the green line shows the performance of the same model when the data is noisy. And they argue that adding relatively realistic noise to the input actually changes the complexity of the problem significantly. But they do show that the model learns over time once it gets to receive enough input data, and more importantly, it shows certain patterns such as the vocabulary spurt. It also, I refer you to the paper itself for other experiments that they have done, but they also show that patterns similar to fast mapping and learning the second labels also appear in this model. So if I want to wrap up this model, basically suggests that the probabilistic representation of word meaning is more suitable than a rule-based symbolic representation of word meaning, because it can deal better with noise and ambiguity, but also it can show various behavioral patterns that are observed in children. Moreover, there are certain limitations to this model and to some other models of word learning. For example, they discard the sentential structure in the input. They don't pay attention to the order of the words. They assume that each sentence is basically a bag of words. And that's something that we have empirical evidence against. We know that children and adults both use sentence structure in guiding their word learning. So this is something that models should also move towards. So I want to summarize the lessons that models such as the ones we discussed in this lecture actually give us. Many of these computational models suggest that several behavioral patterns that we want to find an explanation for can be a byproduct of a statistical learning mechanism that actually exploits the properties of the input data. So things happen because the input data has certain characteristics, and the learning mechanism is used that actually exploits that. Therefore, strong suggestion of these computational models is that the behavioral changes that are observed in children are not necessarily due to a shift in the underlying learning mechanism, but just a byproduct of the statistical characteristics of the process. However, we still have a lot of open questions to point our attention to. For example, most of the existing models do not really use a realistic representation of the visual scene and the semantic information that it implies. The simulation of the semantic representations are very simplistic, and this needs to be improved. Also, most of the word learning models focus on nouns and concrete objects, and they rarely pay attention to verbs and relational terms in the language, or more abstract objects that are not perceivable very easily. Finally, the computational models of word learning have been separated from the other aspects of language acquisition. This is about to change, but this is a major limitation of the existing models, that they don't take into account interaction with, say, sentence structure or nonverbal cues such as gesture and gaze.